Limits of sequences. As the number of terms in the sequence becomes very large, in some cases the terms of the sequence converge to a fixed value, which we call the limit of the sequence. If such a limit exists, the sequence is said to be convergent. A sequence which does not converge is said to be divergent. The sequence 0.3, 0.33, 0.333, 0.3333, ... converges to a third. Consider the sequence Tn is equal to n plus 2 over n squared, where n is an element of the natural number set, so n is a positive whole number. As n increases, the value of n plus 2 over n squared tends to 0. We write this as n with the little arrow and then the infinity sign, comma, Tn, a little arrow, and 0. So what this is saying is that as n approaches infinity, or as n gets closer and closer and closer to infinity, and it's positive infinity, that's important to note, not negative infinity, then Tn approaches 0, or tends to 0, or gets closer and closer and closer and closer and closer to 0, but does not actually become 0. i.e., the nth term of the sequence 3, 1, 5 ninths, 6 over 16, 7 over 25, ... tends to 0. So we can see our graph here. We have the x-axis, which we're calling the n-axis in this case, and we have our y-axis, which we're calling the Tn axis. And we can see the first point is 1, 3. So if we were to substitute 1 into our nth term, or into Tn, so we'd have 1 plus 2 over 1 squared. We'd end up getting 3 as our Tn value. Our output will be 3. If we were to sub in 2 into our formula, or into our nth term, so we'd have 2 plus 2 over 2 squared. We'd get an output of 1. So Tn would be 1. So that's where we get 2, 1 on our graph. And if we were to sub in 3, our output would be somewhere above 0.5. And we can see as we keep subbing in values and our n values get bigger and bigger and bigger and bigger, our output gets closer and closer and closer to 0. So we're going to look at this in a bit more detail. So again, this is our graph. Our x-axis is now our n-axis, and our y-axis is our Tn axis. So subbing in 1, we get an output of 3 into this formula. So Tn equals n plus 2 over n squared. Subbing in 2, we get an output of 1. Subbing in 3, we get an output of over 0.5. So it's quite close to 0.6. We're going to look at these values in a lot more detail now in a second. And we can see that as we sub in higher values of n, so the bigger the n value gets, the closer the output gets to 0. And we can see that our points on our graph are getting closer and closer and closer to the n-axis, which we know is the x-axis. So let's start with 1. So subbing in 1, so T1, so replacing the n's, both of those n's for 1, we get 1 plus 2 over 1 squared, which gives us 3. So subbing in 1, we get an output of 3. So that's where that red point comes from. So that would be T1 on our graph. So 1, 3. And then again, taking our nth term, so n plus 2 over n squared, and replacing both of those n's now with 2. We get 2 plus 2, which is 4, over 2 squared, which is 4. So 4 over 4 gives us 1. So we have an n value. We've subbed in 2 in place of the n, and we have an output of 1. So that's where that red point comes from. So 2, 1. T3 will be 3 plus 2 over 3 squared, which will give us 5 ninths, which is 0.5. And I have a little dot over the 5, which shows that the dot is recurring. So that's approximately equal to 0.5555, which rounds off to about 0.6. So subbing in 3 into our formula, into our nth term, we get an output of about 0.6. So that's where that red point comes from. So for T4, we get 4 plus 2 over 4 squared, which gives us 6 over 16, which is 0.375. So subbing in 4 into our nth term, we get an output of approximately 0.375. So that's going to be our red point there. Then T5 is 5 plus 2 over 5 squared, which is 7 over 25, which is 0.28. So subbing in 5 into our formula, into our n term, we get an output of 0.28. So that's where that red dot comes from. For T6, we get 0.222, which rounds off to 0.2. So subbing in 6 into our nth term, we get an output of 0.2. So that's where that red dot comes from. Then for T7, term 7, we get 0.18 approximately. So subbing in 7 into our formula, we get an output of 0.18. So that's where that red dot comes from. There's T8, 0.16 approximately on our TN axis or our Y axis. T9, there's our red dot for term 9. Then term 10, there's our red dot for term 10. T11, term 11, there's our red dot for where term 11 would be. T12, T13, T14. Hopefully you can notice that all the values, all our outputs, they're getting closer and closer and closer to 0. So we have 0.12, 0.12, 0.10, 0.09, 0.08. So we want to see this number, we should see this number getting closer and closer and closer to 0 because the graph is tending to 0. So 0.08 for term 15 is our output. For term 16, we get 0.07. For term 17, we get 0.06. So again, we can see this number is getting closer and closer and closer to 0. So we're getting closer and closer and closer to 0. The graph is tending to 0. If we choose bigger values for n, so our graph only goes up as far as 17 on the n-axis, but we can choose to input any n value we want. So let's say we went for 100. If we sub in 100, we get 0.0102. So a very, very small number now, very, very close to 0. If we sub in 200, we get an even smaller number, 0.005 for our output. If we sub in 400, a bigger t value again, so term 400, 0.002. So we're getting smaller and smaller, closer and closer to 0. And if we sub in 1,000 even, which is a very, very, very big n number, we get a very, very, very small output, 0.001. But it never actually gets to 0. And you could sub in any number you want for n. So you could sub in 1,000,000, 1,000,000,000, 1,000,000,000,000. It doesn't matter what you sub in. It'll get closer and closer and closer to 0, but it will never actually reach 0. Note, although the nth term, Tn, never becomes 0, by taking n large enough, we can make the difference between Tn and 0 so small it is negligible. In chapter 7, that's calculus, we've already stated that the limit as n approaches infinity of 1 over n, 1 divided by n, is equal to 0. And therefore the limit as n approaches infinity of k over n is equal to 0. Also, the limit as n approaches infinity of k over n to the power of p will equal 0, where p is greater than 0. The following rules as n approaches infinity should also be noted. So this is just our limit notation, just to take note of it. It's not in the formula book, you should be aware of it. So this is in the calculus chapter as well, so we will cover this again in the calculus chapter. So this states that the limit as n approaches infinity of Tn is equal to L. This states that as n gets close to infinity, so as n gets bigger and bigger and bigger and bigger and bigger, Tn approaches the value L. So these are some of the rules. We need to learn these off. So the limit as n approaches infinity of c is equal to c. So the limit of a constant c is c. So if there's no n value, or in the calculus chapter, we'd more so see x's. If there's no variable, the constant just stays as the constant. The limit as n approaches infinity of Tn plus or n is equal to the limit as n approaches infinity of Tn plus the limit as n approaches infinity of or n. So we can see that if we're adding, we just break it into two different parts. For multiply, the limit as n approaches infinity of Tn multiplied by or n is equal to the limit as n approaches infinity of Tn multiplied by the limit as n approaches infinity of or n. So again, it's just broken up into two parts and the multiply goes in the middle. And then dividing, the limit as n approaches infinity of Tn divided by or n is equal to the limit as n approaches infinity of Tn divided by the limit as n approaches infinity of or n. So I'll just zoom in to show you that a bit closer. So the limit as n approaches infinity of Tn divided by or n is equal to the limit as n approaches infinity of Tn divided by the limit as n approaches infinity of or n. In practice, as in Chapter 7, Calculus, to evaluate the limit of a fraction, divide both numerator and denominator by the highest power of n in the expression, and then use the appropriate rule above. Remember that the limit as n approaches infinity of k over n to the power p is equal to 0. So this is something that you have to learn off. So the limit as n approaches infinity of k over n to the power p is equal to 0. So it gets closer and closer and closer to 0. And because the difference is so tiny, we say it just tends to 0. So we say it basically equals to 0, but technically it doesn't actually equal to 0. So the bigger n gets, the closer the limit gets to 0. And these rules, again, in the yellow box, they're just written out over here in blue writing. They're just explained in English. So the first rule, where we have the c's, this is just saying that the limit of a constant c is the constant c itself. So if there's no n's or no x's, then the limit is just the value itself. For the one with the pluses, so highlighted in blue, in English, that's just saying the limit of a sum is the sum of the limits. So if there's a plus in between, we just break it up into two parts. Then the green ones with the multiply. So in English, this is just saying the limit of a product is the product of the limits. So if there's a multiply in between, we just break it up into two separate limits with multiply. And then in pink, the last one, in English, the limit of a quotient is the quotient of the limits. So again, if there is a fraction, it can be broken up into two separate limits divided by each other. So we're going to just have a look at this statement here in a bit more detail. So the limit as n approaches infinity of k over n to the power p is equal to 0. So if we let k equal 1, for example, and p equal to 2, and n equal a large value, we're going to just see what this will look like. So I've just picked two small numbers to represent k and p, and n will be a very large value. So I've just made those values up just to show as an example, but I could have picked any numbers at all. So if k is 1, so our numerator is 1, and n is going to be a big number, so I'm going to start off with 100. And the power, I'm just going to let be 2. So p is the 2, so the power is 2. So 1 over 100 squared is 0.0001. Now if I choose a bigger value for n, so letting n be an even larger value, so I'm going with 1,000, I get 1 over 1,000 squared, which is 0.000001. And if I choose a bigger value again, so 10,000, I get 0.00000001, etc. And I could keep choosing bigger numbers for n, and I'll get smaller, much smaller numbers every time I choose a bigger number for n. So I'm getting closer and closer and closer and closer to 0. So I just wanted to show as an example why this statement is true. So it's not actually equaling 0 ever. It's just getting closer and closer and closer and closer to 0. But because the difference between that value and 0 is so small, we just say that it is equal to 0.